Hello everyone, we are in section 1.4, and in section 1.4 we're going to take a look at the topic of continuity and continuous functions. Now intuitively, on the graph of a function f of x, if there are any sorts of breaks, holes, or jumps in the graph, then that would suggest that we have a discontinuity in the graph of the function. So how is this going to work out? Let's say, for instance, notice in here that we have a jump from this point to the lower point at A. So that would be example of a jump discontinuity. Okay, and then over here I have a hole. I'm looking at part at C on the number line. Right in here there is a hole in the graph. Okay, so this one we characterize as a jump. And of course the break in the graph would be here. Okay, so this is where the break is. Okay, and of course there is a break in the graph at all of them, but more specific kind of break we're looking at is the kind that's suggested by having some kind of a vertical asymptote at that point. Okay, so let's proceed by actually defining each of these discontinuities in terms of a mathematical notation. So let's begin with the following. If function f is undefined at x equal a, then the result would be a hole in the graph of the function. Okay, so the function at that point is undefined. If the limit of the function doesn't exist, if the limit of f of x as x approaches a, d, and e does not exist, then that means most likely there's going to be a jump discontinuity in the graph. And if the limit of the function as x approaches a approaches plus or minus infinity, then we have what we call an infinite discontinuity. In this case, again, we're going to have a vertical asymptote on the graph of the function. Okay, so let's actually define now. We're going to take a look at a definition of a function that is continuous at a point. Okay, so we're going to look at continuity at a point, and let's say at a point we're going to call it at x equal a. That would be our point. Okay, so in this definition we have, let's put DEFN for definition. So we're going to say that a function f is continuous at a point x equals a, provided again, I apologize for this happening quite often. It's my pen, it's not engineered properly. The erase button is right kind of where your index finger is holding the pen, so that's why occasionally this happens where I am actually erasing rather than writing. Okay, at x equal a, provided these three things happen. Okay, so first thing, f at a is defined. Now remember, if f at a is defined, means there's no hole in the graph, right? The second, the limit must exist. Limit of f of x as x goes to a exists. So that means does not exist, and it's not an infinite discontinuity. And finally, in item 3 here, part 3 of this definition, which brings in together parts 1 and 2, the limit of f of x, remember it exists, and it equals to f at a as x approaches a. So if we want to show a function is continuous at a point, we need to show all three of these. However, it suffices to just show item 3, because if you do item 3, then pretty much right here, f at a, you're doing part 1 here, and this would be part 2 if you show that the limit exists and is equal to f at a. So again, all you have to do is just show part 3 of this definition is met for a given problem. Okay. Next, what we want to do is we would like to classify the discontinuities of the graph of a function. Okay. So let's write down classifying discontinuities. Okay, so the first, there's going to be a couple of these. Okay, and actually I'm going to put there's going to be 3 of them. Okay, so the first one that we're going to look at is called a removable discontinuity. A removable discontinuity looks like this. There's going to be a hole in the graph of the function, so this is function x, f of x. Then here's the hole is where the discontinuity is. Now how can we remove this? Well, we can remove it by defining like a piecewise function that assumes a value, whatever the value might be, at point A. Okay, so in that sense it is removed, that discontinuity is removed. Now oftentimes, instead of taking the discontinuity to be outside of that circle, we choose to actually make it go inside of the circle. So let me show you what I mean. Right in here, you see that? If I can define a single point, why don't I define it to be actually on the graph of the function? So this way I won't even notice a change in for all practical purposes, it's going to look perfectly continuous, right? Because once you fill in that hole, the function is just going to look like this. There, that's what it's going to look like. So right in here, that's where the discontinuity was. But again, we don't have to do that. We can just there you go. We can just make it at some arbitrary point, but the point could be the missing point in the graph of the function. So in that sense, that's why it's removable. Now the next kind of discontinuity we're going to look at is going to be let me change my pen, sorry about this. Okay, we're going to look at jump discontinuity. So with a jump discontinuity, the limit does not exist on the graph. Okay, so it would be something like this. Notice the right left hand limits are different. So this is a case where the limit backward e means exists, a line through it means does not exist. The limit does not exist. Okay, so this is going to be the jump discontinuity. And then our infinite discontinuity is going to be characterized as such. And there you go. Now, the way I have this, you could have infinite discontinuity going this way like that, or you can actually have it look like this, or you can have it go down both directions. There you go, from both sides. So those are all example of infinite discontinuities. So you have a vertical asymptote. Okay, so if I make up the graph of a function again here, so let's say I have a function that may look like this. It's going to come here and it's going to bounce, go over here, and then pick up from here, go all the way up, and let's say go down like that. Okay, so you can see now that we have all 3 discontinuities again. Where there's a hole in the graph, this is going to be what kind of discontinuity? removable, correct? Removable. And a single point, by the way, cannot be more than one of these. So let's say, let me throw the horizontal axis here. Let's say this is point A, this is point B, and this would be at point C. So at point A, I can only have one of these three. You cannot have more than one. Now, throughout the domain of the graph, I can have many of these, but not at a single point. So at B, this discontinuity here, this is going to be jump. And again, at C, this one is going to be infinite discontinuity. Okay. So let's take a look at now another example where actually we have a function to work with. So we want to see what kind of discontinuity there is. So here, example, let's say I have f of x is equal to, let's go x squared minus 4 divided by x minus 2. And of course, x cannot be 2 because you get division by 0. But let's define another point. There you go, a single point to be x at x equal to 2. I actually have a value of 3. Okay, so this is going to be my f of x. Now with rational functions, that means a fraction. We always, if we can simplify these fractions, we will do that. So in the numerator, you probably recognize you have difference of two squares, so we can factor difference of two squares divided by x minus 2, the x minus 2's cross, and you get x plus 2. So notice the function actually reduces to a linear function. However, to begin with, remember, x cannot be 2. So when I graph this function, I'm actually going to graph a linear function. This is in the form of a slope-intercept, right? The y-intercept is at 2, and the slope is 1. So hypothetically, this is what the line looks like. Now, at 2, when x is 2, the function is not defined. The line isn't defined. But we have actually, right in here, we have actually defined when x is 2, the value of the function to be 3. So for this one, that's going to be right about here. There you go. And that's where 3 is. So this is 2, that is 3. Okay. There, just to boldface the line. And there you have that. Now, remember at 2 there's a discontinuity, so the line, actually there's going to be a hole in the graph of that line, and then there is a point directly beneath it at y equal 3, and that's going to be the graph of this function. So we want to classify the kind of discontinuity for this example. We're going to call this a removable discontinuity. Okay, so hopefully you follow that example fairly easily. Now let's define continuity on an interval. But before we actually look at definition of continuity on an interval, let's talk about left endpoint and right endpoint continuity. Okay, so let's say I have a graph like this. So in this graph, I have points A, B along x-axis, and right here, notice at B, the function at B, that curve is undefined. So I went ahead and put a point, so this is going to be a kind of a removable discontinuity. It doesn't have to be, by the way. Let me erase it. For what we do, it doesn't matter. So this function, we're going to say that this is continuous at left endpoint. because that left endpoint is included on the graph of the function. In other words, it's in the domain of the function. Okay, and how do we write it? We simply say that the limit as x approaches a from the right of the function f of x is going to be a, let's say, in this or just let's say it's going to be yeah, a. It's going to be a. Okay. The limit as x goes, it's going to be actually f at a, not a, sorry, because a is on the x-axis. It's going to be f at a. Okay, and this is for closed interval from a to b. Now this would be continuous at left endpoint. Now what about continuity at right endpoint? So suppose I have a graph like this now. This would be continuity at the right endpoint. So notice now b is included and point a is not included on the graph of the function. So here's a case where we have a function that is continuous at the right endpoint. Right endpoint. Okay, and how do we write this one? This time we're gonna say for this one that the limit as x approaches b, actually, right, the right hand side of the interval, b from the left of f of x is going to be f at b over the half open interval from a to b. Okay, so there we have it. So now we are in a position to define continuity on an interval. So let me write this. We're talking about continuity on an interval. Okay, so for this one, let me sorry, this thing is in the way. We didn't need this. Let me cut this thing. All right. Okay. And so I'm going to define continuity on an interval. So here's our definition. Our definition is going to say that a function f is continuous on a closed interval from a to b. Notice we are not at a single point now. If three things happen: if f is continuous on the open interval from a to b, and f is continuous from the right at x equals a, and lastly f is continuous from the left at x equals b. That would be the right hand side of the interval from a to b. Alright, and that's continuity over an interval. That's what it looks like. So if I look at, for example, right in here, suppose I have a half circle, and this would be a, and that is b. Okay, so it looks like the graph of a half circle, actually, not a full circle, a semicircle. This is an example of a function that is continuous on an interval, closed interval from a to b. Okay, so now that we have defined continuity both at a point at and also on an interval, let's now take a look at some of the properties of continuous function. Now in our work going forward, we would love to have continuous functions, because these breaks in the graph or breaks in the function cause problems because let's say we want to integrate, the integral may not exist at those discontinuities. Okay, so let's take a look at properties of continuous functions. Okay, that's what we're going to look at. We have a theorem here. This theorem goes like this. We're going to let two functions f and g be continuous. Okay, so if f and g are continuous at, let's say, x equals a, then we have these three statements.
I can learn to understand you much better if I can get
Sorry
familiar
about
with the way.
Okay, so let me go up here and let's see. So part A of this theorem is going to say that f plus minus g is also continuous at x equals a. Okay. In part B, the product function f times g is continuous at x equals a. And in part C, f divided by g is continuous at x equals a. Okay. Now, for part C, where we have a fraction, a rational function really is what that is. G at a cannot be 0 because division by 0. So what happens if it is 0? F over g, let's say it has a discontinuity at x equals a if g at a is 0, because we cannot have division by 0. So at that point, what's going on, we probably have either a vertical asymptote or that's pretty much what that is. It's going to be a vertical asymptote. Okay, now we can actually prove these. They're very easy to prove, but so let's take a look at part C. Okay, so we're going to look at proof for part C, the one that you may have issue with. But once you see how this is done, the parts A and B are very easy. So for part C, we're going to begin with looking at instead of graph, let's say let's take a look at two cases. Case 1, if g at a is indeed 0, means we have division by 0. Okay, if that is the case, then f at a over g at a is undefined, right? That is undefined, and this would imply that there is a discontinuity at x equals a. So that's this part of that theorem. Okay, now case 2 is where the denominator is not 0, right? Case 2, that's going to be the case where if g at a doesn't equal to 0. Okay, now if it doesn't equal to 0, then what we need to do is we need to show that the limit, and this is what, let me write that, what we need to show. We need to show that the limit of f over g is equal to f at a over g at a, right? And just the way it looks in part C as x approaches a. So how are we going to do this? So, well, we know that the limit of f of x is f at a, right? So let me just say this. From continuity of f and g, we were told, remember, we were told assuming that f and g are continuous. That was the very first statement in the theorem. So from continuity of f and g, we're going to deduce that the limit of f of x is going to be equal to f at a, right, as x approaches a, and the limit of g would be, right, the second one, the limit of g of x. Oh, actually, instead of limit, let's use a notation. As x approaches a is going to be g at a, right? That follows from continuity of the two functions. So this would imply that we can write the limit of f of x over g of x as the limit of f of x over the limit of g of x. Of course, I gotta put that pesky x approaches a on every one of these, otherwise the statements are meaningless. So please make sure you also put them like on the exams and stuff, or in general, even in your future courses. Make sure you put that. The x and then the arrow to the right and a. And there you go, so we just proved it. So limit of f of x is f at a, that's again by continuity of f in the numerator, the bottom continuity of g. Now, this part is because of the limit laws, right? Remember, limit of the ratio is ratio of the limits, so that's what that is. So we proved it. We're going to call that QED, right? QED means this is what we wanted to show. I believe this is actually short. This is from Latin. Let me write this just so you have it. The Q in QED, Q stands for quad. Okay? The E stands for erat. And the D is, if I remember correctly, it's demonstrandum. There you go. Demonstrandum. So it's quad erat demonstrandum. That means which was to be demonstrated. That's the literal meaning. I believe that's what it was. Which was to be demonstrated. Usually some folks do that at the end of a theorem. They put a QED. So, and there you go. That's what we wanted to show. Okay, so we're done with that part of it. Now, let's take a look at continuity of two special functions. We're going to look at polynomial and rational functions. Okay, so let's take a look at those two functions. Let me put a box here. So we're talking about the continuity of polynomial and rational functions. Now both of those are good functions to work with. Polynomials are the best ones, and we would love polynomial functions. Okay, so our theorem is pretty straightforward. The theorem says that the polynomial functions are continuous everywhere. Not just at the point, but everywhere along the domain. And remember, the domain of polynomial function is all real numbers. For rational functions, those are fractions, right? Rational functions. It's in form of a fraction where top, bottom are polynomials themselves. So rational functions are also continuous. They're continuous everywhere. With all rational expressions, we always safeguard against division by zero. Okay, so we're going to say they're continuous everywhere. Let's say except where the denominator is 0. Where the denominator equals 0. Again, because we don't have division by 0. And there, so we're looking at two classes of functions that are continuous. Now, what about the function composition? So let's take a look at continuity of function composition. Continuity of function composition. Now remember, our function composition is in the form of f of g of x, right? Which we can write it as f parentheses g paren x close paren close paren. And there you go. You can have g of f of x, and you can have also you can have multiple layers of composition. For us, we're just going to go to one layer of composition here, f and g together. So how do these work now with continuous functions? Okay, so we do have a theorem here. Now the book, by the way, numbers the theorem. I just write them theorem. The numbers don't matter. So let's say the limit of g of x is going to be L as x approaches a. Okay, so the limit of the function exists, and we want f to be continuous, and f is continuous at the value of the limit at L. So in other words, f is continuous at a point, because L is a single value. So if that is the case, then we can write the limit of the composition of f of g of x as x approaches a is equal to f at L. So we just have to evaluate the function at a single point. Okay. Now, we can actually write limit as x approaches a of f of g of x, the composition, as f of the limit of the inside function. Remember, a lot of times, or sometimes, we think about function compositions as inside-outside functions, right? When we have f of g of x like that, this will be my outside because it's on the outside function, and that would be my inside function. So that's what this limit is doing. The limit of the composition is you just take the limit of the inside and do evaluate the function at that limit, because remember, the result of this limit is going to be a number, right? And then you do an f at a number, so you're going to evaluate the function at a single point. Okay. Now, by the way, this is important. This theorem holds for other kinds of limits. So let me put a note for that for you. This theorem holds for, now those other kind of limits are limits of this form, limit as x approaches a, let's say from the left, and then the limit as x approaches a from the right, and then the limit as x approaches infinity, and limit as x approaches negative infinity. There you go. So it doesn't have to be x approaching a. So it could be one-sided limit, or it could be the limit as x goes to infinity. A special case of this composition. This is interesting and useful. Okay, so if we let's say f of x to be absolute value of x, and if we write f of g of x this way, then this is going to be absolute value of g of x, right? Because acting as an x is g of x, right? So f of x, again, instead of x here, we have g of x. So the way the function operates, it takes absolute value of the inputs. Let me actually do this, make it clear for you. This is our input. And there, the input goes inside absolute value, right? Well, this is our input. The input goes inside absolute value. Okay, so f of g of x means absolute value of g of x. So what's the big deal of this? Well, for the special case, we can say that the limit as x approaches a of the composition, let me actually write this, of f of g of x, see that composition, is going to be the same as the limit as x approaches a of the absolute value of g of x. And then you can just actually move the absolute value on the outside and just take limit of g of x. And there you go. And the reason is because what you see here, see that? And this are the same. Right in here. You see that? That's absolute value of g of x. So we move the absolute value outside of the limit. So limit of the absolute value is absolute value of the limit. A lot of times it's easier to find the limit of g of x and then worry about absolute value later. Absolute values can get in the way of doing things correctly. Now, of course, provided this limit must exist, right? If it doesn't exist, then this won't work. So let's take a look. Made up an example for you here. Let's say I want to look at the limit as x approaches 2 of negative 3x plus 4. Simple linear function. So I'm doing limit of the absolute value, right? That's going to be absolute value of limit. You see how much easier it is to just work with the limit. Don't worry about the absolute value. Okay, and in this case, direct substitution, negative 3 times 2, negative 6 plus 4 is negative 2, and absolute value of that is 2. There, we're able to do the limit of the absolute value. Okay, now on the graph, by the way, on the graph, if I was to graph this one, here's how the two are different. Okay, so let me actually graph these for you so I can show you what I mean. I'm trying to compare limit of absolute value versus absolute value of the limit, okay, to show you how much easier even on the graph that is. So the first one is an absolute value function, right? So the graph of this function, let's see, y is 0 and x is 4/3, right? So let's say this is 1, 2, 4/3 is here, and then when x is 0 it's up 4, so the line comes like this and then bounces off, right? This is going to be the graph of this function. This is at 4/3. Now suppose this is where 2 is, okay, and it touches the graph here, and when x is 2, this is 2, right? Because again, I have absolute value of negative 6 plus 4, that makes it 2. So that's what's going on with this one in terms of the limit. Now when I look at the other version, see with this other version, I'm actually looking at a linear function. True? Absolute value is dealt with in the end. So I'm actually looking at the graph of negative 3x plus 4, something like that. And this is where 2 is, right? And negative 2, so we're looking at this one. See the difference on the graph? There's two different things, but because we take the absolute value, the answer is going to be the same. So easier to work with the linear functions. All right, so we're done with this one. Now let's take a look at another theorem. Okay, so in this theorem we're looking at continuity of the function composition at a point. So let me actually write that. This theorem is about continuity of f of g of x of a function composition at a point, right? That would be x equals a, and also everywhere. Okay, now let's see. There's two parts of this theorem, part A, part B. In part A, it goes something like this: if g is continuous at a, at x equals a, and f is continuous at g of a, then the composition f of g is continuous at x equals a. In other words, if f and g are continuous, just about everything you do with them will be continuous. You can form the sum function, difference function, product function, quotient function, right? Ratio function, function composition, all of those will be continuous, which is good. Again, it's good when, especially when we go to differential and integral calculus, when we actually apply these ideas. If G is continuous everywhere, okay, and let me just say so is F. That means F is also everywhere. Then the composition of f of G is continuous everywhere. Everywhere. There you go. So keep in mind, we love continuous function for this reason. Now again, just to kind of prove part B here, let's say I want to prove part B. So the proof of, let me see, actually, yeah, A would be easier. Part B, I gotta do right, left. Remember we did that earlier, we did prove it. We gotta do right, left, and in an interval. So let's just do proof of part A, because at the point is easier. This is just to give you some exposure to formal proving, that's all. So the limit as x goes to A of the composition is what we want to find, right? So this is going to be the limit of f of g of x. That's just using a notation, using inside-outside function, so we can relate to it easier than the fog notation. Now, limit of a function composition is going to be outside function f, function of limit of g of x, right? Inside function. We had that from earlier theorem, right? And this would be simply what f, remember limit of g of x is going to be g at a, isn't it? Because the function is continuous. And this is the very definition of fog at a. So in effect, we showed that the limit of composition exists. The function composition at a is defined, and that the limit is equal to that. Remember parts 1, 2, 3? So we just showed part 3 of that, which implies the other parts 1 and 2 also. Okay, so there, we're good with this one. And the other thing, this is important also. The absolute value also. The absolute value of a continuous function is continuous. Okay. Alrighty. Now from this, we're going to look at, we're almost done, folks, with all the theorems and stuff that we want to talk about. We're going to finish this section and of course look at some exercises here shortly by intermediate value theorem. Okay, hopefully you're following all of this stuff here. They're not difficult or cumbersome, it's just the passing phase. We got to go through this. We're going to look at intermediate now value theorem, or IVT for short. Intermediate value theorem. Now this is actually an interesting theorem, and just to give you a little background here, this intermediate value theorem is actually the corollary of another theorem, of an important theorem. It's the corollary, means a direct result of another theorem, and that theorem is called Bolzano's theorem. Okay, named after Bernard Bolzano. That's the gentleman's name, Bernard Bolzano. Okay, actually, his name is quite lengthy. I'll write his full name for you. You'll be amazed of this name. But he's known by Bernard. Okay, Bernard Bolzano, and he actually Bolzano's theorem. It was done in early 1800, so early 19th century. I believe the timeline is about 1817, 1818, something like that. Okay, where this Bolzano's theorem was proposed by Bernard Bolzano. Okay, so now here's his full name, by the way, just to kind of get a break from what we've been doing. His real name is actually lengthy. I challenge any one of you to have a name like this. No way, no how. His actual name was Bernardus. Okay, it was Bernardus Placidius Johann. Now we have many people, I've seen nowadays students that have 4 names like Anne-Marie Finberg Smith, something like that. But this name, Bernardus Placidius Johann, and I'm not done yet, Nepomuk. That's the other part of his last name. And finally, Gonzal. Check this name out. How about that for a name? It makes my name seem a lot easier, huh? So anyway, that's his full name. Okay, and he was pretty a smart gentleman. He was actually Bohemian and very smart. He earned his PhD, I believe, at the age of 23. Now, one thing, by the way, also, I forgot to mention this when we talked about the epsilon delta definition of the limits. Remember that? The precise definition of the limit. So this is kind of interesting. I'm going to write it down just so you have it, okay? You're not going to be tested on it, and it's not in the book, okay? So who came up with like epsilon delta definition, right? Well, the epsilon delta concept, let me just write that. The concept was due to Cauchy. So Augustine Cauchy actually came with the concept of epsilon delta, but he actually never gave a definition of a limit, but he used epsilon delta in the proofs of limits. Okay, so the concept was done by Cauchy. And then the modern statement that we actually use, okay, and also before I go to modern statement, so epsilon delta, I think I'm going to go with 1817. I feel pretty good about this date. In 1817, the definition was given by Bolzano. Okay. So we're talking about over 200 years ago, something that happened, and we're still studying that today. Okay. Now, the modern statement that we talked about, for the absolute value of f of x minus L, absolute value of x minus A less than delta. That modern definition, let me just say modern statement. That statement that we already know about was actually defined by Karl Weierstrass. So there you go. This is another mathematician, Karl Theodor Weierstrass. And in fact, later on, let me write this before I misspell it. Weierstrass. There you go, Weierstrass. Okay. And his name was, I think there's another thing, I think it's Theodor, it was Theodor Wilhelm. Yeah. I'm going off my memory here, that's why. Theodor Wilhelm. And again, he was the mathematician in the early to mid 19th century. And in fact, Weierstrass is known as the father of modern analysis. Now, I will show you this function. It's an amazing function, the Weierstrass function. when we go to next chapter and we talk about derivatives. I'll show you this a very cool function that Weierstrass has come up with, and it's amazing what this function is. Okay, so Weierstrass actually didn't graduate from university. He attended it, but he couldn't get a degree. Isn't that amazing? But then later on, because of his scholarly work, he was awarded an honorary PhD, I believe, in Berlin. Okay, and he actually proved the intermediate value theorem. Okay, so for that reason, the intermediate value theorem a lot of times is known as Bolzano-Weierstrass theorem. Okay, so anyway, sorry I went on a tangent, but it was a good break from the norm, from what we've been doing. So let's actually look at this intermediate value theorem. Now we're going to state the theorem without proof. Okay, the proof is beyond the scope of our course, so we're not going to look at the proof. So here's what intermediate value theorem says, that if f is continuous, so we need to have a continuous function. So if f is continuous on, let's say, on a closed interval from a to b, and we're going to let m, and m is any number, and that is between f at a and f at b. Now remember, f at a, f at b, these are on the y-axis, right? So m is actually on the y-axis. Inclusive, then there exists, remember the existence modifier, there exists at least one, it could be one or more, at least one number, we're going to call it C, one number C, inside of that closed interval from A to B. Remember this symbol? F at C equals L. Remember, this symbol means such that f at c is equal to L. So pretty interesting, you know, or harmless, almost intuitive theorem. So let me just draw something here for you, and suppose I have a function that looks like this. Well, let's say this is where A is, and we're going to make this to be B. Here's your XY coordinate system. Okay. Now, f at A exists on the y-axis, and let me stretch this up further, and this would be there. This is going to be f at B, right? Now this other number m is between f at A and f at B, so m is along the y-axis. So we are guaranteed, no matter what number you pick between f at A and f at B, there's going to be at least one value along the x-axis where f at that number is going to be m. So this would be like my C1, C2, and C3. There we go. And this is where B is. And that's all. That's what intermediate value theorem tells us. But then we have another theorem that is actually the consequence of intermediate value theorem. Okay, so it's kind of like a corollary to this theorem. And this theorem is very powerful. This theorem says that if f is continuous on the closed interval from A to B, remember it's corollary of the previous theorem, so it's going to have a lot of similarities to it. If f is continuous on a closed interval, and if f at A and f at B are non-zero, okay, or non-zero, and have opposite signs. So they're going to have different signs. Okay, opposite signs. then in that case we can find there exists at least one solution. Okay, there's at least one solution of the function f of x equals 0. That's amazing. That means we can actually solve this function, solve this equation. And that's going to happen in the a to b open interval. So there you go. This is a very powerful theorem now for us all of a sudden. And let's say I'm going to move my function like this now. So this is b, and this is going to be my a now. Okay, so right in here, and right in here. So L equals 0 now, right? If f of x is equal to 0, the function value is 0. And f at a, this is f at a, is less than 0, right? Negative. F at b is positive. The function is continuous. So because it's continuous, the transition from negative to positive, it has to go through the x-axis. It cannot suddenly jump it, right? For example, this is what I mean. Let's say it's negative. It comes here. And then right here it jumps. See, there's no x-intercept. And this is f at b, isn't it? And let me make this f at a. Right? So this is a f at a, and call this b f at b. This is my x. Now, so we're not allowed to do that. Right? The function isn't allowed to do it because here, this is discontinuous. So the function isn't allowed to do that. We were told the function must be continuous. That means there are no holes, jumps, or asymptotes in the graph of the function. And there you have it. Okay, so we are done as far as our theorems go. Sorry, it's kind of boring just looking at these theorems, but it's important that we have these. One other theorem. Let me make sure that this other theorem I'm about to tell you is indeed in your book also. Okay, actually there's no other theorem. We're done with the theorem. So we're gonna now actually take a look at some examples. Okay, so let's begin with this example. In this example, I want to find let's say a constant. Find a constant. We're going to call it k. Okay. So that we're going to make a function continuous. So the function will be continuous everywhere. Everywhere. Okay, now let's say here's in this example, I'm going to make this function to be a piecewise function. Let's say we have 7x minus 2, and the other one will make it like quadratic, and let's say x less than or equal to 1, and then let's make this one x bigger than 1. Okay, so if I actually graph this now for values of x less than 1, the graph behaves like behaves as in a line, right, for less than 1. So let's say here's where 1 is, and there. So it's going to behave with for x less than or equal to 1, it's going to behave as a line. So, and the slope is 7, so this is very steep. And hypothetically, let's say it goes like this. Okay, and right there, when x is 1, 7 times 1 is 7 minus 2 is 5. So there you go. The other portion of this line is up here, right? But we don't need that because our domain is only for x less than or equal 1. So that's the graph of the line. Now, the second part of that is going to be a kx squared. Remember, this is a parabola. K is a constant in front of a parabola. Our parabolas look like this. That's x squared. k is just a constant multiple, which causes a parabola to either become flat or narrow and possibly reflect, right? If k is less than 0, it reflects. If k is between 0 and 1, it becomes flat. Greater than 1, it's going to be narrow. But the point being is that I have a parabola, and I'm going to assume in this case k is positive, right? We're going to assume k is positive. Now k cannot be negative, and here's why k cannot be negative. Okay, just watch me here. If k is less than 0, that means the parabola opens downward, doesn't it? Right, like negative x squared, for example. So for any negative k, the graph's going to look like this. True? So if that's the case, then we don't even have a function in this case because we failed the vertical line test, right? So we can't have k negative. K has to be positive because we need to go above 1, right? So this is 1. We're going to look at beyond 1. If this is the case, let's say if k is negative, and here where I'm at 1, we don't need this portion of the graph anymore of the parabola, right? So this piece is gone, and I'm just gonna have that portion. Now notice, if k is negative, this is what's gonna happen, isn't it? And at 1 we actually have an open circle, right? It's gonna look like that. Well, looks like a jump discontinuity from here to here. That's a jump discontinuity. Okay, so k cannot be negative. I'm just trying to justify that k cannot be negative. Okay, so assuming k is now positive, with k positive, we want the parabola to, again, the parabola cannot be doing this, it cannot do that, it has to go through this point, it has to go through 5 there. This would be the only acceptable parabola. The parabola has to go through 5. Okay, and this is only good for x greater than 1. So here's where x is 1. So that means this portion of the parabola we don't need, and this part we don't need. And here it is. So what do we need to do in order to make this continuous everywhere? In order for that to happen, the parabola has to go through 5, correct? So what I'm going to do is I'm going to let kx squared, the equation of a parabola, remember this is the y, right? Y kx squared, I'm going to set it equal to 5. That's going to happen when x is 1. So k times 1 squared equals 5, so k must be 5. Therefore, the parabola is 5x squared. Again, that portion of it goes here, it comes right back, but we don't need that part. Okay, good. So we're done with this one. There, that's what I had, I believe. All right. And now let's take a look at some of the exercises in your book. Okay, so let me bring up the page of the book and then we'll see what's in the book. Okay, let's take a look at some of these exercises. Now in exercise number 7 through 26, the question reads, find the numbers, if any, where the function is discontinuous. Remember now, polynomial functions like such as number 7, that's continuous everywhere. Rational functions, these are numbers 9, 11, 13, 12, 10, 8. These are continuous everywhere also, except place where denominator is 0. So we're going to take a look at number 12 in a moment. And then let's see, we will take a look at maybe number 16. Okay. Number 14, look at absolute value. Remember, at some point in our lecture, I wrote down that the absolute value of continuous functions are continuous. So inside absolute value, number 14, you have polynomial function, right? In here, that's a polynomial function. Well, that's continuous, so absolute value of a continuous function is continuous. And because polynomials are continuous everywhere, so in number 14, the composition of would be like f of g with absolute value. It's going to be continuous for all x. We'll take a look at number 16. Don't worry about number 18. Number 18, you're looking at the greatest integer function. So we're not going to work a lot with these later on at all. We don't work with these. You're not going to work with them in your second and third semester calculus, so I'm not emphasizing on those. We'll give you a break. So let's take a look at numbers 12 and number 16. Okay, and I have those right in here. Okay. And number 14, we actually mentioned. Number 14 is continuous everywhere. So, the question said find discontinuities. So for number 12. In exercise number 12, because it's the irrational function, right, in the form P over Q, you have P of X over Q of X, a rational function. Therefore, we're going to set the denominator equal to 0 and solve it. Now, this is factorable, right? X minus 3 times x plus 1 equals 0. Correct? So we said each factor equals 0. X must be 3 or negative 1. So those are the discontinuities. It's discontinuous at 3 and negative 1. And what's going to happen in the graph, when we look at these later on, you're going to have two vertical asymptotes. Number 14, there's no discontinuity. Number 16, let's take a look at number 16. Again, in number 16, I'm okay with 2x. That's polynomial, right? Linear function. Those are always continuous. So we're going to look at this one. So let me actually write it. In number 16, f of x is 2x plus x plus 1. Don't get LCD or do anything amazing. So this is actually in the form of like g of x plus h of x, right? Here's my g of x, here's my h of x. So we got sum of two continuous functions which are continuous, which becomes continuous. So this is continuous. 2x is continuous. So I'm just going to look at the second function. The only way the second function is undefined if we set x plus 1 absolute value of that equal to 0, right, in number 16. Now, absolute value of x plus 1 equals 0. That means x plus 1 is 0, right? So x must be negative 1. This is where the function is discontinuous at that point. Okay, so it's pretty easy so far. Let's move on and look at the page of the book again. Okay, I'm looking at number 22 now. In number 22, and let me get my marker so you can see. I'm looking at this one. There you go, number 22. Now, in number 22, we have a rational function. True? And let's see, x squared plus x minus 3. That is factorable. Oh, okay, good. We'll do number 22 in a minute. That one is a good one. And well, let's see. Oh, we have secant and cotan pi x. So let me see. I think I missed a theorem here. Before we go on further, I'm looking at in here. Okay. And these are trig functions. Oh, I think that's the theorem that I'm missing. Let me actually go back and take a look at the theorem, make sure I covered it. Okay, perfect. Let's take a look at number 22. Okay, so in exercise 22 again we want to find the discontinuities of this function. So in number 22, first we're going to, let's see if this is factorable. Divided by x minus 2. Believe it's going to be x minus 2 times x plus 3. Right? Two numbers multiplied to negative 6. Negative 2 times 3. Negative 2 plus 3, 1. So that looks like the right combination. Okay. So this is just a linear function. It reduces down to a linear function. So number 22, therefore f of x is simply x plus 3 and then 5. And x cannot be 2 and x is 2. Notice, by the way, in this x plus 3, 2 works perfectly fine. But to begin with, we weren't allowed to have 2 because of division by 0 before we simplified it. So we look at the natural domain here. Okay. And so this is easy now. All I have to do is just, let's see, there's no discontinuity here. The reason, because here, this is continuous from negative infinity to infinity. And of course, x cannot be 2. And then that hole in the graph at x equals to 2 is filled by defining at x equal to the value of function to be 5. In other words, if I graph this function now, here's how this function is going to look like. Right, that's the graph, the linear function. At 2, the function is, the line is undefined because it cannot equal to 2. But then notice the way this function is defined. At 2, the linear function is undefined, but the author has defined at x equal to 2 a point to be 5, so he's actually removing that discontinuity by inserting a point into that missing hole. So the actual graph, the final graph, looks like this. You and I will not even know that there was a discontinuity there, because the only point that was discontinuous at 2, the value of the function is 5, was covered, the hole was covered by defining a piecewise function. So this is actually continuous everywhere, because again, x cannot be 2 here, but then x equals to 2 in another form. So this one is continuous everywhere. There are no discontinuities. So number 22, it is continuous from negative infinity to infinity. Okay. Now let's take a look at number 24. In number 24, f of x is equal to negative absolute value of x plus 1 for anything but 0, and when x is 0, he defines it to be 0. Now the function itself at 0 is 1, right? This function, when you plug in, you get 1. So he's actually defining a different point. Now, what does the graph of this thing it looks like? Let's graph this absolute value function. The graph of absolute value of x looks like this, right? A v-shaped function. That's absolute value. Negative absolute value of x, you have a reflection, right? That's negative absolute value of x. And then plus 1 gives the vertical shift. And there is a graph of this thing. Now, when x is, and we're told x cannot be 0 for the function, the top function, so you have a hole at 0. Okay. And then he's defining the function to have a value of 0 when x is 0. So he's defining it. Let me use a different color. There. See that? He's defining it to be right there. So this is, again, the function is continuous let's see. Yeah, that function is discontinuous at x equals 0. Okay. We have a removable discontinuity, but he chose not to remove it. Up here, he removed the discontinuity, but he didn't do it down there. So this function actually, because f at 0 does not equal to 1. Why 1? Because 1 is the limit of the function. Remember the definition of continuity at a point. A function is continuous at a point if f at a equal to the limit as x approaches a of f of x. Well, the limit is 1, right? The limit is 1, but f at 0 is 0, right? 0 does not equal to 1. So this one is discontinuous at x equal 0. Alright. Now, I was surprised. That's why I was thrown off, because he doesn't mention about continuity of trig functions in this section, or at least I couldn't find it. But keep in mind, all trig functions are continuous on their natural domain. That would be sine, cosine, tangent, cotan, secant, cosecant. So when we look at, for instance, let's say number 26, cotan pi x. Let's take a look at this one. And let me switch my pen. Okay. And we're going to do number 26. Number 26, f of x is cotan pi x. Now the graph of cotangent, if you recall the graph of cotangent, let's see, it's gonna look, let me fix this line. Okay, sorry. There. So graph of cotangent, cotan x, which is ratio of cosine x over sine x, is undefined where sine is 0. So we're going to look at zeros of sine that are k pi. So at those points, cotangent is undefined. We have vertical asymptotes. And then the graph looks like this. True? So here's the case where all the zeros of sine are points of discontinuity for the cotangent. True? So for exercise number 26, discontinuities are at k pi. Discontinuities at x equals k pi, where k is an integer. K is integer. Right? Like 0, 1, 2, 3, and the opposites -1, -2, -3, and so on. Because cotangent is periodic, right? That's why. Here's the other portion of that cotangent, and so on and so forth. This is at negative pi. Okay. So we figured this one out too. So remember, all your trig functions are continuous over their natural domain. Let's go and find other examples here. Okay, let's take a look at number 30. Okay, so I'm going to copy number 30 into my notes now. Okay, let's take a look at exercise number 30. In exercise number 30, we want to find the value of k. It's kind of like the earlier example that I did. We want to find the value of k that will make the function continuous everywhere, right? That's from negative infinity to infinity. So we could go ahead and graph it just to kind of see what's going on, but without graphing, we can also do this. So remember, at x, it looks like x gonna approach 2, right? Because that's what these two suggest. So we need, for the two limits, the limit of the two functions to be equal to each other at that point, at point x equals to 2, in order to have continuity everywhere, right? So I'm going to say for this exercise that the limit of kx plus 1, right, that limit has to equal to the limit of kx squared minus 3. Now, x is not going to approach the same number, right? X doesn't approach 2 exactly 2 because the first function is good for less than or equal to 2. In other words, it's only defined. There you go. We have a linear function. Let's say this is my function. And this is where 2 is, right? This function is only defined up to that point. So for the limit, for the line, it can only approach 2 from the left. True? It can only approach 2 from the left because it's not defined for higher than 2, greater than 2. So I'm going to make the limit as x approaches 2 from the left. Now, for the parabola, x must be greater than 2. So this is what the parabola now looks like. Let's say here's -3, and I'm assuming k is positive. K is negative, it will turn the other direction. But without loss of generality, we can assume that. Okay, so there you have it. Now, for this one, again, this parabola is only good at above 2. So let's say this is where 2 is. Okay, and I don't need this part of it now. So this parabola is only good from here upward. Okay, it's only good over this domain. That means this little piece of it right here we don't need. Alright, so you see that? Therefore, the limit for the parabola has to approach 2 from the right. X approaches 2 from the right. Good, so all we got to do is equate the limits. Now the limit of kx plus 1, right, kx plus 1, as x approaches 2. You plug in 2 for x, you're going to get 2k plus 1 equal to the limit. Plug in a 2 for x, 2 squared 4, you get 4k plus, or minus, sorry, 4k minus 3. And then we can solve this for k, subtract 2k from both sides and add 3, we get 4, so k is 2. There you go, we found k. K is indeed a positive number, k is 2. Okay. Now, let's take a look at the trig ones, okay, because those are a little trickier. Alright, so in number 32 now, again, we want to find the value of constant c that will make the function continuous. This time it's not from -infinity to infinity, it's at x equal 0, right? So continuous at x equals 0. So that means I'm gonna have to look at the limit of x approaching 0, right? Looks like that's where the cutoff is. Now again, this cotangent function is defined for negative values, so x has to approach 0 from the left, right? Because it's less than 0 means negative, so we approach 0 from the left. Okay, and then I'm just gonna go x cotangent of kx, right? And the other one is going to be a c. Okay, that's interesting. And then we're gonna set that equal to the limit as x approaches 0 from the right now, because for x greater than 0 you have to come from the right to reach 0 or near 0 of x squared plus c. Now this limit is easy, right? X goes to 0, 0 plus c is c. Now on the left side, as x approaches 0, right, we get what are we gonna get? Let's see, if I plug in, I get 0 times k times 0 is 0. Cotangent of 0 is infinity, right? This is interesting. So we have 0 times infinity. This is actually an indeterminate form. Okay, so I'm not gonna say the answer is 0. That means we gotta work this out. Okay, so let's take a look at closer at the limit of x cotangent of x kx as x approaches 0 from the left. Now cotangent is the ratio of cosine to sine, right? So this is the limit as x goes to 0 from the left of x over, I'm going to go sine kx, and this would be cotan kx. So there's my cosine over sine. Now, looks like something that we have seen before. Remember the limit of sine x over x? So except this is now sine kx. Now in the numerator I have x, so I'm going to multiply by k. The idea is to make these look the same, right? Kx and the argument of sine. Now I just multiplied by k. In fact, let me do this. Let me use a different color marker so to emphasize the actual insertion of k. See, I'm creating a k here. So I'm going to multiply the bottom by k. Multiplying top by k, bottom by k. Again, the reason I need to do that because these two must be the same to use the theorem we had for limit of sine x over x as x goes to 0. It's for that reason. Okay, now I can actually go back to my marker. So there's my sine x over x. And then, of course, and I'm so sorry, this is cosine, not cotan. And then I have simply cosine kx over 1. Alright. Now, limit of a product is product of limits. We know this limit is 1. And then cosine of kx, when x is 0, you get cosine of 0. Cosine of 0 is 1. 1 over 1 is 1. Aha. So c is equal to, looks like 1 in this case. Let me, actually it's going to be 1 over k. In this k right in here, that's going to be there. There you go. It's 1 over k, not 1. Right? That red k in the denominator. There. Tidy up this thing. Okay. Only kx over sine kx. That limit approaches 1. You still have k in front, right? This k is what this k is. Alrighty, we're good with this one. So c is going to be 1 over k. And the question said find c, right? Find c. So that the function is continuous at that point. The answer is c equal 1 over k. Let's take a look at another example. Okay, so I'm here on the next page of the exercises. Let's take a look at number 36. In number 36, the question says determine whether the function is continuous on the closed interval. Now, number 36, we have a rational function. Remember, rational functions are continuous everywhere except where denominator is 0. Well, the denominator of this fraction is 0 when t is plus minus 3, correct? So, negative 2 to 2, we are fine because we are inside of that negative 3 to 3, right? In other words, let me write it there. For this one, t cannot be 3 or negative 3, right? So we are fine. Negative 2 to 2 does not include 3 nor negative 3. That interval is good. So, yes, the function is continuous. Okay. Now, something like, for example, number 38, maybe, something like this. We want to find the intervals where f is continuous. Okay, now in number 38, here we have a function in the form of g times h, right? So remember, if two functions are, because they're using f, so I'm using g and h. If two functions are continuous, the product of continuous functions are continuous, right? So square root of x is continuous. Well, let's actually work that one. Okay, so let me pause and grab this problem, and then we work them. Okay. No. Sorry. I'm not sure what I just did. Oops. Hold on. Okay, so I think this is better. I copy and pasted it into my note, this segment of the exercise. Let's take a look at number 38. In number 38, we have f of x is root x times x minus 5 to the fourth. So we have two functions. We have g times h. Now, root x is continuous, right, over its domain. And h is a polynomial function, fourth degree polynomial function. So it is also continuous, therefore you're looking at product of two continuous numbers. The domain of x is greater than or equal to 0, correct? So in number 38, 0 to infinity, it says just find the interval where f is continuous, because h is continuous negative infinity to infinity, right? And g is continuous 0 to infinity, so the intersection of the two intervals is going to be 0 to infinity. Okay. You go with, because again, if I go negative, for example, see, h has no problem handling negative numbers, but the square root of x has problem handling negative numbers. So that would be the answer to number 38. Okay. Let's take a look at number maybe 44. In number 44, we have f of x is 1 over x. So again, this is an oblique hyperbola, right? So we have this one, and we're looking at sum of two continuous functions over the respective domains. 3 root x over x minus 2 squared. So we have rational numbers in here, right? Not rational numbers, I'm sorry. So we have this fractional x expression. It's not a rational function because the square root of x is not polynomial. So we just have an algebraic, really. The fraction is an algebraic function. That's all that is. So let's take a look at the domains. For 1 over x, x cannot be 0, right? For square root of x, x must be at least 0, and in the denominator, x cannot be 2. So each of these will give us an indication of what the domain should be. We want f to be continuous, right? Over what intervals? So in number 44, let's see. The interval looks like is going to be, because it's the sum of the two now, it's going to be from 0 to 2, union 2 to infinity. Okay, and the reason again is it's like that. It's got to be positive because of the square root. That's why we start from 0 here. Not negative numbers aren't allowed. But then this one says x cannot be 0, so we have parentheses at 0. And then this other restriction says x cannot be 2, so these coming next, and each of those must be parentheses because they're not included. So again, we have to make sure that we keep all functions, all three functions happy. And by happy here means we want to make sure that all three functions are defined in their natural domain. Now, in number 46, we have sine x over x, right? Now, that's the ratio of 2, number 46. Number 46 is a ratio of two functions, a trig function and an algebraic function. Okay, so in the denominator we know x cannot be 0, but x is all real numbers in the numerator, so there's no problem in the numerator, right? The numerator can be anything. It's just x cannot be 0. Therefore, for this one, the interval of continuity will be negative infinity to 0, and then union it with 0 to infinity. And that should do that one. For something like number, again, 48, for instance. Number 48, f of x is 2 cosine x. Now, domain of cosine are real numbers, right? So no problem in the numerator. Domain of sine is all real numbers also. Okay, so again here, negative infinity to infinity. This one, negative infinity to infinity. Therefore, this is continuous everywhere. And there's no way the denominator can be 0, right? Because in order for denominator to be 0, this should be negative 5, so it adds with 5 to become 0. But there's no way 2 sine x would be negative 5, because sine is between negative 1 and 1. So there's no way 2 sine x becomes negative 5. So we don't have to ever worry about 0 in the denominator. And let's finish this segment with number 50. Number 50, we want to find the limit as x approaches negative 1 of absolute value x squared negative x minus 2 over x plus 1. Okay, now if we can simplify this, we need to simplify it, and the numerator actually ends up being factorable, right? So it's going to be x minus 2 times x plus 1 over x plus 1 absolute value. We can cross out x plus 1s. Now remember, limit of absolute value is absolute value of the limit. So we're going to take advantage of that theorem and just evaluate limit of x minus 2. Plug in negative 1 for x, we get negative 3. So the answer is absolute value of negative 3 or 3 in this one. Okay, let's take a look at another segment in the exercises here. Okay, let's take a look at this one now. The first one, number 51, that one is pretty straightforward. The question says define the function at a. So to make it continuous at a. Okay, so we just remember, to be continuous at a point, f at a must equal to limit, right? So for example, let's take a look at number 50. I want to do 52, but in number 52, this thing is probably factorable. Yeah. Boy, okay. Number 52. First, let me factor this one. Okay. Now, I'm going to use, let's see, synthetic division. Okay. I'm trying to find factors of 2x cubed plus x minus 1. So I'm going to go 2, 0, 1, negative 3. Remember this work, everyone, from your pre-calculus class. And I'm going to choose 1. Remember, it's the form x minus c. So I'm guessing c to be a 1. Why? Because there's x minus 1 in the denominator. I bet you those can cancel. Bring the 2, 1 times 2 is 2, add 1 by 2 is 2, add 1 by 3 is 3, add. Perfect. See, that was a good hunch. So the remainder of synthetic division is 0. That means x minus 1 is a factor. So let's do number 52 now. It's easy now. Number 52. Our function f of x is equal to, the factored form is going to be x minus 1, and then the last row of the synthetic division table tells us that this is 2x squared plus 2x plus 3. That's the quotient in synthetic division. Okay. And then in the denominator I have x minus 1. The x minus 1's cross out. Okay, so what do we have here? We just have 2x squared plus 2x plus 3. And again, in order for the function, see, we want to make it continuous at a. To be continuous at a point, limit and the value of the function at that should be the same. So I'm going to write that. We want limit of f of x equal to f at a as x approaches a. That was the condition for continuity at a point, right? So for all of these in this segment, that's what you want to do. Now, let's do limit. So what will the limit be as x approaches 1? We are given a is 1 in number 52. And the function is 2x squared plus 2x plus 3. And that should equal to f at 1. So plug in 1 for the limit. You get 2 and 2, 4 and 3, 7. Right? We get 7 there. That's for the limit. Now we already know because at 1, right, f at 1, there you go. F at 1 has to be 7. So what we need to do is this in number 52, therefore. We need to define, right? It says define the function. Okay, so we're going to define the function to be this. 2x cubed plus x minus 3 divided by x minus 1. Right now this function is discontinuous at 1. Agree? Because division by 0 occurs when x is 1. So we're going to say x cannot be 1. Now we can actually make it continuous at that point. There you go. If you define the x at 1 to be 7, it will fill in that hole that's in the graph of the function at that point. And there's no vertical asymptote here because, remember, when we actually reduce this function, it actually reduces to a quadratic function. It reduces to this function up here, right? So at x, and x cannot be 1 means in this function at x1 there will be a hole in the graph of that parabola. Anyways, we're done with that one. Now, if you wanted to do something like number 54, boy, there's so many of these, and but might as well do it, right? Because in a regular class we have 2.5 hours. So this isn't bad. My video is almost an hour and 40 minutes now. So, and I'm sure you guys don't mind, right? The more the merrier, so you have something to bounce off of for your homework. Okay, now for this one again, if you plug in a 4 in the denominator, you get division by 0. In fact, at 4 you get 0 over 0, right? In the form of the limit, that is. But this isn't a limit, this is just a function, right? So for number 54, again, we want the limit of the function of 4 minus x over 2 minus root x as x approaches 4 to equal the value of the function at that point. So let's find this limit first. So this is the limit as x approaches 4. And we could multiply the top and the bottom by conjugate of denominator. Okay, or you can factor 4 minus x. If you factor the 4 minus x, it's going to be 2 negative root x, that may be easier, times 2 plus root x. It doesn't really matter. Or you can multiply top bottom by 2 plus root x. Okay, but if I just factor the numerator as difference of 2 squares, these cross out. And we have the limit as x approaches 4 of 2 plus root x. Directly substitute for x, we get the limit is 4, right? So that's what we want to define the function to be. So we're gonna let f of x be what the original function is, right? But remember, in the original x cannot be 4. So we're going to let that x be 4. When x is 4, the value of the function is also 4. That's this number. Pure coincidence, folks. This turned out to be the way it did. Okay. So there's number 54. Let's take a look at the trig function, one trig function, and we'll look at maybe one last, or one from intermediate value theorem, and that should do it for us. Let's take a look at number 56. What do you say? This one, number 56. Sorry. Okay. In exercise number 56, f of x is equal to sine squared x divided by 1 minus cos x, and a is 0. Again, direct substitution. Let x be 0, because that's what a is. You get cosine of 0 is 1, 1 minus 1, 0. So f of x is not defined at 0. So far we know this until there. This is what we know so far. That x cannot be 0 because you get division by 0. So we want to know now, when x is 0, what should we define here is to cover that discontinuity to make it continuous, right? So we need to find the limit. The limit as x approaches 0 of this time of sine squared x over 1 minus cosine x. And remember, folks, when you're working the limits in this chapter so far, we haven't gone far. We really did limits involving trig functions in one section. I think it was section 1.2. So remember the limit of sine x over x and the limit of 1 minus cosine x over x. Those are really the only two limits that we know about. So all of these trig functions must somehow turn into one of these. Okay. Now, for number 56, I'm going to multiply top bottom by the conjugate of the denominator. That is 1 plus cos x. Okay. And then once we do, in the denominator, we're going to get difference of two squares. And that's going to be sine squared x. And note there's a sine squared x in the numerator and 1 plus cosine x. Now for this one, it turns out I don't even need to use those theorems, sine x over x and 1 minus cosine x over x, because these cross out and all I have is 1 plus cos x, right? So this is going to be equal to the limit as x goes to 0 of 1 plus cos x once I simplify. It's easier to simplify this way than to carry the limit in every step. So now plug in a 0 for x. Cosine of 0 is 1. 1 and 1 makes 2. And that's what we want to put in here. So we're going to let that be 2. There. Now doing that, it makes the function continuous. It removes that discontinuity. It's removable discontinuity. Let's take a look at last exercises. I want to look at something in the way of intermediate value theorem. So let me go back to your exercises, and there you go. Exercises. Okay. I'm looking at up here. Okay. I am over here now. There is at least one root. Okay, let's do maybe one of each of these. How's that? Now the difference being, in this one, it says use intermediate value theorem to find the value of c such that f at c equals m. So they give us an m. No biggie. We can do that very easily. 63 to 66. It says use theorem 7 to show. Theorem 7 is the intermediate value theorem, to show that there is at least one root of the equation. Oh, remember I mentioned a corollary to the theorem. That's very important. Allows us to solve equations. That's what that is. It says show that there is at least one root. Roots are solutions. So that's what we want to do. Okay, let me copy and paste this one, and then we'll work one of each of these, and that'll be the end of this lecture. Okay, so let's take a look at numbers 60 and 66. In exercise number 60, again, the question reads, use the intermediate value theorem to find the value of c such that f at c is equal to m. Okay, so in number 60, the interval goes from 0 to 3 and m is 3. So we need to, for number 60, we need to find f at 0. Remember, our interval is from a to b, and in this case is 0 to 3. So I'm doing f at a and I'm doing f at b for the intermediate value theorem. Now f at 0, you plug in a 0 here, you get 6. True? And f at 3, again, you plug in a 3 for x. And for this one, f at 3 is going to be 3 squared, negative 4 times 3 plus 6. That's going to be 9 minus 12 plus 6, so that's going to be 3, right? Okay, and m is, what is m? M is 3 in this case also, right? So, in this case, we're going to go f at 3, right? F at 3 less than or equal to 3 less than or equal to f at 0. True? That's how it lines up. Therefore, there exists a number c such that f at c is equal to 3. Right? Now we need to find the c actually here. So we're going to actually f at c, we're looking at this one. F at c means now you plug in a c into the function. Remember, this is the function. You're going to put a c here and there. So we're going to get the c squared negative 4c plus 6 equals 3, and then we can solve this. Subtract 3 from both sides, and this would be factorable. The factored form is going to be what, c minus 3 times c minus 1 equals 0. And from this we pick up c as 3 and 1. See, we were able to find at least 2 values. Okay. And there we go. Looks like we're good in this one. We're able to find the value of c. So that's how you work this one. Let's see, maybe let's try to do number 66. Okay, let's try number 66. Now in number 66, we want to show that there is at least one root, means one solution. Okay, so that means we're now looking for opposite signs. Okay, opposite signs. For f at a and f at b in number 66. That's what we're doing. Now, this is, let's see, the function on the left is a polynomial function. This function is continuous, right? And from 2 to 3, this function is also continuous. Okay, that's good. Now, let's do f at 2, and f at 2 is going to be what? When we plug in a 2 for x, right? Oh, how are we actually doing this? Let me show you this. X to the 4th minus 2x cubed negative root x minus 1 equals 0. Okay, so that's the equation. Therefore, our f of x is going to be x to the 4th negative 2x cubed minus square root of x minus 1. Okay, now if I plug in a 2, f at 2, that's going to be 2 to the 4th minus 2 times 2 cubed negative square root of 2 minus 1. 2 to the 4th and 2 to the 4th. These cross out, so you have negative square root of 1, which is negative 1. Okay, so f at 2 is negative 1. Now f at 2 is less than 0, which is, let me write it here, f at 2, which is -1, is less than 0. That's at a. Remember, to show that there is a 0 between f at a and f at b, the sign of f at a and f at b must be opposite. So f at 2 at a in this case is negative. We're hoping f at 3 would be positive, and that's the indication of a root or a solution between 2 and 3. So let's actually now do f at 3. F at 3. So I'm plugging in 3 into this function. That's going to be 3 to the 4th negative 2 times 3 cubed negative square root of 3 minus 1. 3 to the 4th, that's 81 minus 3 cubed times 2, that's 54 minus square root of 2, right? That's going to be 27 minus root 2. Now square root of 2 is about 1.4. 27 minus that is definitely positive. So there you go. F at A is negative, F at B is positive. True? So that means from those two, based on that theorem that we had, I guess it's theorem 7, it said in the exercise, yeah, there's got to be at least one root. At least one root. Remember, roots are solutions to that. Okay, and that's what we have here. So let's see. Okay, so looks like we are done with this section. The video took almost 2 hours to complete, so that's not bad. Now remember, for these long videos, I know you get tired listening to me for 2 hours and watching this for 2 hours, so please, what you want to do is you want to piecemeal this. So for long videos, most of our videos are going to be this long anyhow, okay, because I would like to do a lot of exercises. I'm sure you'll like that. So what you might want to do is you might want to just kind of take it little chunk at a time. So watch it for 5, 10, 15 minutes maybe, then take a break, come back, watch another piece, and so on, so it doesn't get to be boring for you. But anyhow, we covered a lot of ground here, so that's good. Everything looks good, and we are done with section 1.4. We only have one more section and we'll be done with chapter 1.